sponsored by IEEE Indonesia section. Today's lecture's title is about MEMS technology and its applications. Now I'm going to introduce speakers today's. The speaker today is Professor Kukjin Chun, PhD, fellow IEEE and fellow IOP. He is a full professor at Department of Electrical and Computer Engineering, Seoul National University, Korea. He obtained a bachelor degree in electrical engineering from Seoul National University, Korea in 1977. He obtained master degree in electrical engineering from University of Michigan, US in 1981, and he obtained PhD in electrical engineering from University of Michigan in 1986. His current activities, this year he is as the Vice President of IEEE Member and Geographical Activity, MGA. He is also Director of IEEE Boards of Directors this year. In 2019 until 2020, he was the chair of IEEE Region 10 Nomination and NNA Committee. In 2017 until 2018, he was the director of IEEE Region 10. He was also the director of IEEE Board of Directors. In 2015, he was the president of Korea Sensor Society. In 2012, he was the president of IEEE, of IEEE Korea, IEEK. His research interests are in integrated sensors, intelligent microsystems, and MEMS processing technologies. He received so many awards. So I just pick 3 awards. I cannot read one by one. So in 2017, he received the Order of Science and Technology Merit of Korea. In 2013, he received Haedong Awards, IEEK, and in 2008, he received a Best Paper Award from Korea Sensor Society. So actually, he has many activities and rules, so I just highlight some of them. Now, welcome to all participants online via Zoom and YouTube channels. Thank you for attending this lecture sessions. You can interact with the speaker, so you can write your comment and also question through Q&A in this box, in Zoom box here. So thank you. Now I will invite Prof. Kukjin to deliver a talk. Prof. Kukjin, time is yours. Thank you.
Okay, thank you. Thank you, Nia, for a nice introduction.
Yes.
So can you see my screen?
Yes, perfect.
Okay. Yeah. Hello, everyone, and good morning. And it's my great pleasure and honor to have this time on MEMS technology. Actually, MEMS technology is a kind of new area these days. It started in the 80s, well, I'll talk about some of the technology and some of the applications of that. And I really thank the University of Indonesia, Professor Wisnu and the Professor Nia, for this opportunity. How can I move it? It's being shared and okay, thank you. Yeah. So as you can see on the right of the screen, the kicker strikes the ball, and the ball, tells you some of the information like the stroke, launch angle, spin, or velocity of the ball, and it's transmitted through Bluetooth. And, as in the bottom, the PCB is embedded inside this ball with the 12 anchor points and with the suspension ties and the charging coil for the power. And that this ball has a compass module, and then accelerometers, and then magnetic sensors with a different the spec. So there are several of them, and detecting those the kicker is performance, and it's it has a BLE 4.0 for networking, and then the lithium-ion battery. So this is one application of the MEMS. And another example, you can, well, I think all of you are using inkjet nozzles, from HP or Canon or other, Epson or those companies. And there, inside of it, you can find, the structure similar to the ones on the top, on the left, in the red color. That there is a chamber, and then the reservoir and the schematic or the cross section of that chamber is on the right side, part of it, so that it contains the ink. And then there's a heater underneath or either side of it, and then it's heated, and then it pops up through the nozzle. And the nozzle is made of the MEMS technology here. And then you need thousands of nozzles in a very condensed areas. So that's the merit of the MEMS technology. And at the bottom, you can see the very high aspect ratio structures, and it's from the organic material. So, by using MEMS technology, you can make a very high aspect ratio, meaning that the ratio between the horizontal and vertical, dimensions are very big, like 100, that you can find, you can make a very the versatile, the structures, as in the photo. And on the right side, this is very, I would say, the interesting and famous, and you may have seen this in the cover page of the textbook, that this is the accelerometer, from the American company. And here we have a sensor in the center, and then other part of this chip, which is a 3x3 millimeter, is that all analog circuits. So we'll get into this, again. But anyway, this is again another example, in the sense that you have all the required circuitry associated with the sensor, and the sensor is made of MEMS technology, and other parts is made of a conventional CMOS IC technology. So that's a combination of the already established semiconductor technology, and then if you add some more feature from the MEMS technology, then it'll make a pretty big, the change, and then it'll make a lot of contribution, to your company. So what is MEMS? That's well, actually, this MEMS acronym made in the 80s, and it stands for Micro Electro Mechanical Systems. Because in the 80s, most of the applications are on mechanical systems, but nowadays it's expanded to other areas. And here micro, it's a microfabrication, and electrical characteristic, and mechanical characteristic, and then systems. So MEMS, is frequently used in this area. And if you go to Europe, they use microsystems instead of MEMS. And if you go to Japan, And a lot of people use a micro machine instead of MEMS. So they basically represent, the same kind of discipline, or research areas. And here, as in the bottom of this chart, you can find the signals, like in the nature, that the MEMS technology can handle. Like the heat, the thermal, and then the fluid flow or sound or electricity or magnetism, and then biology, chemistry, and light, and even the quantum mechanics can be dealt with. And in another the language, MEMS is a transfer function, such as a you can change or transfer from the pressure gauge to the very small chip, which is packaged in a ceramic package here, that you can make a 1 millimeter by 1 millimeter chip for pressure sensing, which is compared to the tens of centimeter of that pressure gauge. And the tilt sensor can be converted to the so-called IMU, inertial measurement unit, or that the microphone, which is again a big one on the left side, can be converted to another 1 milli by 1 millimeter chip, embedded in your the cell phone, in most of cell phones now. And at the bottom, even people use the animal for gas sensing. But you can, make a MEMS chip, which is pretty small, to replace it. So it's a kind of replacement of the existing the devices to a basically the silicon chip. So it's like an IC. So usually MEMS technology is used in a system that that provides providing the feedback, as in this chart, that the sensor detects the signals of the electrical, mechanical, optical, fluidic, chemical, or thermal, or even biological, and then that transduces that signal or that energy to this electrical signal. Usually the current or voltage, or sometimes the charge, and then it's again they convert it sometimes to the electrical signal, and then digitized, and then it's fed up to this microprocessor unit, so that it makes a decision, and then it gives an order to the actuator to do something. And it's the feedback to the sensor again, so that it makes a closed loop for a the whole signal processing. And sometimes the RF, the transmission or communication or networking, the function is added, so that the whole scheme, is composed. And it started with as in the bottom, the discrete sensor. So again, like in the previous page, it started with a discrete sensor and the microstructures, and then from the 60s and 70s, and then in the 1980s and 1990s, it's getting more complex. So the people talk about integration of the sensor and the microstructure, and the integration of the sensor and the interview circuits. And then nowadays, with the help of the nanotechnology or a new material process, or the flexible electronics even, people are talking about the cell-powered connected microsystems. So in the distributed systems. Okay, so the IoT is one of the application in that area. Okay, historically, in the 90s, Bell Lab, they discovered a very important the processing technology, which is called isotropic etching using KOH. And it's a wet etching technology, but it was very useful at the time because there was no integral circuit fabrication, the machine tools. And then in the 60s, Honeywell, developed a pressure sensor. Is the silicon membrane and formed by the anisotropy. So this the silicon, again, studied a new age of application other than those integral circuits. And then in the 70s, the Stanford, I think initiated, some profound research in this area. And then, the MIT or Berkeley or the Michigan, and other universities, and the couple from the Europe, joined this research, and it really grows. And in the 80s, the Kurt Peterson, he received the Medal of Honor from IEEE a couple of years ago on this activity. And some, the students in the United States formed the startup company in the Silicon Valley. So that's a kind of start of the MEMS related, company there. And then Kurt Peterson, has been trying 6 companies so far, and 4 of them are very successful. So and then nowadays, you're using inkjet again. So these days, everybody knows the sensor, not the MEMS, but the sensor. Right? So when I came back to Korea 30 years ago from the United States, I took a taxi, and at the taxi driver, they talked about the memory device. Fine. And then after 30 years, the Korea is quite well known, in the DRAM business. And nowadays, people talk about sensors. So I hope, the sensor area will grow, like that one. But nowadays, the sensor is called like a smart sensor or intelligent sensor, meaning that it employs the MEMS technology, not only that one, but nanotechnology or semiconductor technology. And usually it's, implemented, realized in a system on chip, the basis, meaning that one chip has all the system. And then, in many cases, it has a software, and then the circuitry for logic, communication, and data storage, and then data processing, and then compensation, and then decision making. So, again, it gives a high functionality and precision and value. So it's evolving now. And in the market, the market, it's growing again as other technology. And now we are in the 2020, which is the center of this chart. And then if you, look at the future, then you can see the very big portion here, which is, on the top, and that's the RF MEMS. So that portion will be really growing, pretty much. And then at the bottom side, you can find the inkjets and pressure sensors and microphones, and they are, so and so. So they just take the pretty much the same amount, but the portion is, becomes smaller. And the emerging, the products are RF MEMS or oscillators or resonators, and the environmental MEMS, like the dust, these days, and then microfluidic devices. So those are the emerging the areas now. And the players, Broadcom. So in the sensor or MEMS area, the communication, the company in the mobile, applications has the top portion, followed by the Robert Bosch, the automotive parts manufacturer, and then microelectronics, company, and then TI, and then some startup, and then HP, and so on. So there are the major players, and then you may need the foundries sometimes, so you can find these foundries as well. And in your smartphone or cell phone, you can find at least a couple of these devices in this chart. That from the right, you can find a mirror or autofocus function, or there's some display enhancement, or the switch or tuner, or the oscillator, or the speaker, or the temperature sensor, thermal imager, and haptic interface, or humidity sensor, or the pressure sensor, or that kind of environmental sensing as well. And in the car, you can find more. Every car has a airbag nowadays, which is the law. So that's one of the big applications now. And then microphones for noise cancellation. And to the left, pure injection, and then the distance detection for the collision avoidance, or airflow sensor, pressure sensor, proximity, mainly from the radio technique or other type, and then brake pressure sensor, tire pressure. Again, TPMS is legally required, in some countries, and then exhaust sensors and as well. So these sensors are very, necessary for the autonomous the driving. So that's more sensors will be used in the future. And in the biological areas, you can also find the many different types of sensor or actuators, and it's called a lab on a chip. Like SoC, it's a one chip contains a whole lab, bio lab, such that it has a function of a cell separation, concentration, and then the detection, and then the signal processing, and then for a the RF, the networking as well. And it detects protein, DNA, all cells nowadays, so that it has a the microfluidic the function with a valve, pump, or mixer in a small scale. And then for this one, for the biological applications, material has been expanded to the glass or the polymer. So nowadays, MEMS is not only the silicon domain, but it's very wide. So again, the MEMS fabrication, has an advantage of the batch fabrication. So batch fabrication offers the potential for great cost reduction, manufacturing in high volume, so that the silicon, is often used for these devices. And then the lithography, offers some micron precision on dimensional scale, and then thin the thin film deposition or etching are, these technology are used in this IC fabrication, but also in the MEMS. And then wafer bonding technique, which is unique for MEMS, is also, sometimes required to allow the patterning of the third dimension. So it'll be a 3D structure than 2D. That's for a moving parts of some applications. Okay, so the MEMS is a kind of cousin of the IC technology. You can find a lot of similarities as well as the difference there, such that initial investment on the equipment is required, and patterning or batch process or process integration, are pretty much the similar and value-added industry. And the IC is, takes care of the electrical signal, and then in 2D dimension. But the MEMS, is a electrical, mechanical, biological, or other type of all different types of the areas in a 3D structure. And then the IC fabrication, is similar, but here we are looking at a rather low accuracy than this IC. These DRAM technology or microprocess technology, are using 5 nanometer technology or 10 nanometer technology, but MEMS is still using 2 micron technology, or 1 micron technology, or a rather low accuracy, and it requires a special equipment for special fabrication. So in terms of the fabrication, the thin film growth, doping, lithography, dry etching, metallization, planarization, they are pretty much the same, except some of them in MEMS technology require thicker, the dimension. But the differences are in the bonding, electroplating, and then using different substrate, and the thick photolithography. So for these ones, the MEMS technology may need a different set of tools or machines. So that's another challenge in this area. Okay, the materials, basically it's a silicon, as in the microelectronics. So that's for microstructure. And then the silicon means a single crystal silicon. And then polycrystal silicon is also used, as in the IC. And then, some insulators like silicon nitride or silicon dioxide or PSG. And then metals, like aluminum, molybdenum, or nickel, for the magnetic, the magnetic properties. And then it's expanded again, to the other areas, like nickel ferrite, it's a ferromagnetic material. And then the PDMS, perylene, polyimide, like organic material, the polymer materials. And then photoresist quartz or aluminum nitride, and then other type of piezoelectric materials. And so this, well, I don't think we have time for this one, but anyway, the aluminum nitride, is realized in a tens of nanometer thickness. So if you think of the 12-inch wafer, the diameter size is 12-inch or sometimes 8-inch. And then if you're talking about 50 nanometer, thick aluminum nitride all over the surface, that's the accuracy of this, the application. So that's used for basically these days for a filter in the RF MEMS area. So that's a new technology, new application, but it's very powerful application, so that the aluminum nitride on top of the silicon, makes a fortune, these days. And Broadcom is the company, which uses that technology. Okay, and I'll get into the fabrication a little bit, so that we have a micro machining, bulk or surface. That if you want to make a nozzle for this, the inkjet inner, then the cartridge, then the nozzle is shown in the left side, where the process sequence to make this nozzle, on the right side, with the cross section of the wafer. So you start with the silicon wafer at the bottom, as in the number 1, the process. And then you put another silicon layer with a doped, meaning with an impurities, and then you put the photoresist, and then you make a pattern there, and then you make as in the step 2, you make an etching of that layer, which is another silicon layer. And then remove the resist after the process, and then plane it. And as in the step number 3, make a thin layer, deposit a thin layer on both sides, and then make a pattern on the bottom side, and then with this the bottom side, you make a anisotropic etching, so that and then after the etching, you remove that silicon nitride, which is deposited. Then you'll get this nozzle. So that's a fabrication process, and it's called a bulk micromachining, because it deals with the whole substrate itself. But sometimes you don't want to touch the substrate and only the surface of it. Then so it's like the IC fabrication mainly, and it's called the surface micromachining. And here, at the bottom, as in the cross section, you have a silicon substrate, and then you make you deposit a oxide, or you grow the oxide, which is usually the 2 micron thick. So it's a very thick oxide, and it has a stress. So you can see the warping, of the wafer after this process. Anyway, so sometimes you put another layer, to compensate that stress. Or you make a pattern there, and then you put a polysilicon layer on top of that, which is blue here, and then remove the oxide, which is orange color here. Then you can see the on the top portion, you can see some free moving cantilever, okay, with the anchor on one end. So you can do a lot of things with this cantilever by applying the voltage there. So this is called surface micromachining, because the substrate is not touched, but only the modification on the surface side. And here you use a oxide in orange color as a sacrificial layer. So it was there, but it's removed, at the end of the process, so that it makes a gap between that cantilever and the bottom. So if you put a electrode on both sides, then you can apply the voltage here, and you can make a resonator, the oscillating, beam. So that's used, that can be used for a gas sensor or a biological sensor, to determine the weight of a very small quantity. For example. So in the 1987 was the start of this technology actually, and at the time a group of people developed a one device called comb drive resonator, and it's a one of the breakthrough in this area. So this kind of structure is used in many applications nowadays, so that you have a comb on the top and the bottom, the comb structure, and then folded beam, which is a spring here, and then you can see the anchor side. So this kind of simple structure contributes quite a bit, and it's very often used, in many applications. And the comb, you cannot see the bottom, but it's the etched into the vertical direction, so that there are two sets of comb. That one side is fixed, and the other side is connected to this folded beam, which is the spring on the left, and then that's the other end of the spring is fixed. So the left in this parallel, the plate structure, the left plate is moving, the back and forth, so that the gap is moving, it's changing. And if you apply the voltage between those two parallel plates, then that'll make a change in the capacitance, and they'll make a change in the charge, and that gives us some force, and then it's restored by the spring, which has a constant K. So after a few rather simple mathematics, then you can find the force and the relationship between that force and this applied voltage. So as in the first equation, if you want to increase the force, you need to enlarge the area. The area is the length of this comb times by the depth of the comb. That's the area. So if you want to increase this, the sensitivity of this structure, then you need to increase the area, meaning that you need a deeper etching, deeper, you need the structure, in more depth. So that gives a challenge in the fabrication. And the G is a gap between those two parallel plates. And that's a thickness of this, sacrificial layer. So that's another fabrication challenge. You need if you want to increase the Fe here, then you need a smaller gap, meaning that you need a thinner the deposition or thinner layer there. So that's another challenge for the fabrication. And then applied voltage. So in many cases you want to have a lower the voltage V here. So for that one you need to have a very fine fabrication technology, meaning that the fine tools and everything, from the water to the gases, and the chemicals, and then so it's more expensive. So that's a challenge, in this area. And if you move that, the plate with a plus charge, to the right side, and after a certain point, that this relationship collapses. that's called a pull-in point. And then that pull-in, VPI, is is given at the bottom of this chart. So you don't want to operate this one, over the pull-in voltage. So if you want to make more freedom, you need higher the V, and that gives you a the bigger G, and then the smaller A. So which is a the trade-off. So you need a trade-off between those force and this pull-in voltage. Okay. Another example is the Standard National Lab in the United States, developed this technology using 5 layers of polysilicon, and you can see the moving gear and the some of the anchors and the connected part, so that you can provide a linear or the circular motion out of this very sophisticated structure. And how to remove the anything underneath this gear so that you can move, that's kind of secret. Okay, well, this is done in a clean room, as in this layout. This is one example, in my university. It's called the Inter-University Semiconductor Research Center, ISRC. That on the left side, that's a mainly CMOS fabrication area, and on the right side, it's a MEMS, fabrication area, and some compound semiconductor people, use the same MEMS area as the equipment. So they are isolated because usually MEMS use different types of material, which which is basically a contaminant to the CMOS fabrication. So they're isolated, but they're in the same facility, so that we are very lucky, to have a full set of equipment, for the fabrication of the some of the CMOS device, various small ones or the MEMS devices. And this facility is shared, with the universities and all the other research sector in Korea. And it was the first one, 30 years ago. And so it was, pretty much used by the researchers now, in Korea in the early days. But nowadays, I think about 10 locations have similar the facility for the fabrication, so people can have a some the freedom to use this equipment. So since UI, University of Indonesia, is a leading university there, you may want to think about this one, like the sharing facility, open and sharing facility, for researchers in Indonesia in the area. Okay, so I'll just spend. Okay. I guess I do have about 20 minutes, or 15 to 20 now.
Yes, you still have time.
Okay, good, yes. Good. Yeah. I'll just quickly. So from now on, I'll just quickly over some of the processing steps, and then get into the sensors area. Well, the fabrication is done, by using several different types of the fabrication process. And the basic is the oxidation. Why silicon is used for DRAM or for any microelectronic, the devices. That's because of this oxidation. Because this one, this process gives a very thin. If you want to make a 5 nanometer technology, you need a the 1 nanometer thick oxide. how do you make it? So that's a challenge. But anyway, this oxide, is very, very good, with a high breakdown voltage and very, the uniform oxide can be grown out of this technology. Well, as in the photo in the left, this piece of equipment, it doesn't look very complicated, and actually it's not. The nature does, the whole thing. So as in the center, if you just put a wafer on top of the quartz boat, which is cleaned, and then put it into the the chamber, and which is heated, excuse me, which is heated, then those oxide will grow from the nature. But again, in this tube, it's heated up to 900 degrees C or 1000 degrees C. And sometimes there is a flows of water, which is vaporized. Then that'll expedite the oxidation. Okay, so basically, so silicon is provided from the wafer, and then you put a very clean oxide, and then it'll make SiO2. Okay, so it's very simple. And then sometimes, actually many times you want to put some impurities with a controlled amount. Then you implant ions, okay, on the in the device area. So the machine is pretty long and big because it deals with very toxic, like boron or arsenic, phosphorus. They are very toxic gases. So there are the sources on one end, as in the diagram on the right, and then the ions are emitted, and then they are separated, in the magnet area, and then it goes into the acceleration tube, which applies either 30 kilovolt or 100 kilovolts. So it's a very, very high current, high voltage machine. So it's protected, in many areas, in many ways. And then, as in the center, you load the wafer, there, and then you get the very controlled dose of the impurities, either boron or the mainly arsenic, the atoms, in your wafer. And that the boron will make a p-type mobile charge carrier, and the arsenic will make an n-type mobile charge carrier. And that this doping, will put the minute quantities of impurities, and then that modify the electrical characteristics of the material, like a resistance. Okay, and then usually out of this process, the impurities are implanted in the normal, the distribution. And another type is the thin film deposition, and for the metal or for the dielectric. And for the metal, people use evaporating process, which is a thermally evaporated metal atoms are adhered on the surface of target, or the sputtering. And actually in the manufacturing, the sputtering is more, the frequently used, because it's fast and very, even, the uniform, and then chemical vapor deposition or physical, the CVD, is also used, so that you have a solid the substrate, and the gas flows in on top of the surface, and it nucleates, and it makes an island, growth to make a some film, and then there will be others are exhausted out. Okay, so for this one, you need some the specific type of gases, and then you need some temperatures of up to the 800 degrees C. So from the 600 to the 800 degrees C, you can make a very uniform and thin layers of the dielectric material insulators. So this is a deposition, process in which precursor materials are introduced into a heated furnace, and the chemical reaction occurs on the surface of the wafer, resulting in the deposition. And the silicon is from the silane, SiH4, and then also for silicon oxide, nitride, aluminum oxide, all kinds of different types. And LPCVD or PCVD are used, and then LPCVD provides excellent uniformity, and then PCVD processes at lower temperature, below 400 degrees C. So depending on the application, you use either one. And if you go to the IC fabrication area or MEMS fabrication area, the pattern transfer or photolithography is the most expensive and most the useful and the most the contributing the technology. So like EUV stepper nowadays, that costs the $200 million per piece. So for making a one IC fabrication, like a Samsung, you invest 30 billion, for the campus of the fabrication area for DRAM in near Seoul, and that has a separate building of those lithography tools. So this is the most challenging and very expensive the process. So pattern transfer consists of two parts, and the photo process. The desired pattern is photolithographically transferred from an optical plate, which is called a mask, to a photosensitive film coating of the wafer, which is called a photoresist. So at the bottom of this chart, you can see the green area, which is a photoresist, and the violet area, and you can see the transparent area. So that violet piece is a optical plate, which is called a mask. So a chemical process of removing materials to create a pattern. So there are two-step process. And then it's like a photographic process, in the old days, not the digital ones. So contact prints are made when the negative is placed directly on the sheet of photosensitive paper. And then usually people use 4:1 reduction, for a here. And then on the right side, you can see this. The cross section of the wafer, so that you have a silicon substrate at the bottom, and then you have an oxide, on top of it, and then photoresist, which is a rather a clear area, and then on top of that you have the mask. A part of it is opaque, and a part of it is open, transparent. And the light goes in through the transparent area and makes a chemical reaction. And then after developing, you have an opening there, and then you make an etching, to make the change in the oxide layer. Okay, so in the stepper you can find a lot of lenses, and then excimer laser light source, and then you put a mask in between the lenses, okay, as in the diagram on the left. Okay, CMP is also used in MEMS and IC fabrication. It's a polishing, process to make a flat surface before deposition of any layer. And so if you want to make a flat surface, you just do the CMP. It's a chemical mechanical polishing process. And before bonding, and then the planarization. And then dry etching, that's a dry etching technique for solid material in gas phase. And then the chemical reaction, with the reactants, occur there. And then plasma chemistry, it can be used for etching. And so that you can find the CF4 or SF6, mainly, or sometimes Cl-based, chlorine-based, the gases are used. So for this, Bosch developed this process that is called a deep RIE, as in this chart, that it gives a very deep etching, as in those examples, that you can make a pump drive out of this deep RIE etching, with a very deep, the etching into the substrate. So the whole silicon substrate is etched away, by using this technology. And it's quite unique for, the MEMS technology, and it's from the Bosch. And bonding, is also used, so that on the right side, you have a one silicon substrate at the bottom, and then another silicon wafer or the glass, on the top. So two pieces are bonded together, okay? So to make a 3D structure, so that the whole is made on this bottom portion, which is trapezoid, the area, and then another the cavity is made on the top portion, so that the pressure is the transferred from the bottom to the diaphragm on the top to make a pressure sensor, okay? And then the MIT, has worked on this microturbine, for about 10 years. And then, so for that one, you need a 25 wafers bonded together, okay? And then make a, to make a certain power and, combustion there. So you need a lot of cavities, and, so they're all the bonded together. And I think because of time, I think I need to skip either it's called a pre-CMOS or post-CMOS or interdigitated. Because of the CMOS and the MEMS process, it can be, so you make a, as in this slide, you make a MEMS first, and then cover it and protect it, and then make a CMOS, or vice versa. Or you make a interdigitated, the process between CMOS and MEMS. So, that some layers like a doping or dielectric layers are shared, in this process. So we'll get into the sensor area, and then I'll, introduce 4 different types of sensors, in this session. And the first one is a pressure sensor. Again, it's a very old technique, but it's a kind of a textbook, in this area. That's a bulk micromachinery pressure sensor, and it's using piezoresistive, the property of the silicon wafer, meaning that means the change in electrical resistance due to the mechanical stress. So if you apply the pressure, as in the diagram here, from the back side, from the hole, and then to this diaphragm, on the top, and that's a about that can be a 2 micron thick, or that can be a 10 micron thick, or even 100 micron thick, thickness. And then that deflects due to the pressure. And that deflection, creates a stress, and then that stress is converted into resistance. Okay. And for that one, you need a thin diaphragm, and then you need some the pair of the resistors there, which is made of some doping. Okay, and then that's it. So it's quite simple, but it gives a very sensitive device. But here, the membrane deflection is less than 1 micron. Okay. For that one, on the right side, that shows the process sequence that you from the silicon wafer, and then you need another epi layer, so-called, another silicon, and then you deposit the insulator on both sides, which is black here, and then diffuse the resistor or by doping on the top, 2 islands, and then make a contact on the left side, and then put a metal on it, and then make a pattern of it. And then from the backside, you etched away some portion of it until this epi layer, and then put a the glass, which is orange color here, by anodic bonding, so-called wafer bonding. Then that creates a pressure sensor. And there, the piezoresistivity coefficient is a 4th rank tensor. So it's you are talking about solid state physics here, that the electric field is related to the current with the resistivity law, and then the stress sigma here, and then piezoresistive coefficient, which is a tensor, the phi here. So this phi is a property of a material, the silicon in this case, silicon single crystal. So the phi, that gives the sensitive devices. So if you put those the black the resistor in the front page, either longitudinal direction or transverse direction, you can make the resistance change delta R over R, which is proportional to this phi, and then the stress sigma. Okay. Other type of pressure sensors are you can use a polysilicon, which has a temperature up to the 200 degrees C. Usually, silicon, is used until 150, 100, 120, because at the 180, and the PN junction does not exist. Okay? But the polysilicon, you can go up to 200 degrees C. And then sometimes people make a capacitive pressure sensor, which is basically the two the parallel plate. And then the plate, the diaphragm, deflects pressure, and then that's for a low power system, and that provides a low sensitivity on the temperature change, which is a good. And the second, the example is accelerometer. Again, this is a 3x3 millimeter chip, and then the sensor is at the center. So accelerometers have been developed with many different types of the principle. And here, this one is a capacitive, actually. And then MEMS accelerometer provides high performance, low cost. So that's the killer application of this technology. An analog device, developed the monolithic. This is called a monolithic, the silicon IC plus the MEMS sensor area, the polysilicon accelerometer, which is a on-chip IC. And then they claim it in 1989, but the first shipping was done in 1995. And if you make a little bit modification on that one, then you can make an inertial grade accelerometer. So my team worked on this one, for the missile, the application. And it has as in the bottom of this figure, it has two identical Prof mass, and then the comb drives, again. And it's called the double-ended tuning fork type, and it's using a resonator, for the minimum forces and torques. And then differential output scheme is used for noise cancellation. And then the resolution was up to 2.5 micro-G for inertial grade accelerometer. And for this one, you have a resonant type, oscillating type, the beams. And then if any acceleration is applied, then they change the frequency of the oscillation. So it provides a digital output directly from the sensor. And it's a vacuum packaged because there is the moving part. So it has a silicon wafer at the bottom, and on the top, is the glass wafer analytically bonded. And then in the vacuum environment. And as the time goes by, the outgassing of some materials, can happen. So this vacuum packaged, and there's a gathering materials, which is a titanium in this case. So it lasts quite a long time. The fabrication, what this one shows the cross section of the fabrication of the wafer. So again, the silicon wafer, and then some the deposition and then patterning, and then the different layer deposition and patterning, and then another one. So it's a sequence of a deposition and etching, okay. And then on the right side, you put the glass bonding on top, which is green here, and then make the CMP for structural layer, and then do the deep RI etching, so that you can have a mass, on both ends, and then anchored, and then the moving comb drives, in the center. Okay, and then this comb drive, is moving, to make an oscillation. So from the airbag at the bottom, to transportation, and to the IMU, for defense applications, there are many applications. And the third type is gyroscope. Gyroscope detects a rotational angle or angular velocity. And there are many applications, of these gyros. And I think, some of you already used these gyros. And automotive or consumer electronics use rate grade, the IMU aeronautic application and navigation grade. And for the MEMS technology, there are many different types of gyros, like fiber optic gyro, ring laser gyros. But for this gyro, usually MEMS technology use a vibratory gyros. So that detects rotation and uses vibrating mechanical element with no bearing, and easy for size reduction with a batch micromachine. So this vibratory gyro is basically an accelerometer that detects a Coriolis force or Coriolis acceleration to calculate the rotation rate. So F equal ma, and A is an acceleration, and then A is a 2 times the angular velocity times the physical velocity. So that on the right side you have 2 gimbals, and then either to the moving into the one moving into the X direction for the driving, and the other one moving into Y direction for sensing. So there is no cross coupling between those two, Then the proof mass is in the center, and then they are connected, through the spring on both sides, to different. Okay. So the silicon micro machine, the vibratory gyroscope, use a polysilicon surface micro machine gyros, and it provides a reasonably good Q factor, and then orientation independent because it's a polysilicon. So on the right side, you can also find a lot of electronics, and at the center, you see the moving part, which is a sensor area. And then there are two identical, the device there again, for the reducing the noise portion, so that it can provide a high signal to noise ratio and then parasitic capacitance reduction. Okay. So that this one, it's called a BiMEMS, meaning that MEMS plus IC, which is a bi-CMOS process, bipolar CMOS process, and the surface micromachining. I think it gives a reasonably good performance there. So this is good for the automotive applications. Actually, it's developed for the. But if you want to go to another level up, then as in the bottom, you can make a very fancy device. Like in the photo, you can see the mass at the center of this circular structure, and then springs, many springs connected to this rotating, either right side or left side, or vibrating the circles. And then as in the small inlet, you can find the white electrode area, and then the rotating, the mesh-like structure, so that there is a submicron gap between this white electrode and the rotating mesh-like structure. So it provides a very small capacitive operating gap, and the thickness of the mass is defined by the bulk micromachining, but the gap is defined by the surface micromachining, meaning that you grow the oxide there between those two, and then remove the oxide, and that'll give you the gap of those two moving parts. So it's called a submicron gap gyros. Okay. And the last example is the fluidic bead cube embedded portable CMOS biochip for immunoreaction monitoring. Well, okay. So for this chip, it's a portable diagnostic system, and then the ELISA is possible, with a pH sensing ISFET. ISFET is another chemical sensor measuring the pH of a material, and then CMOS temperature sensor, and the fluidic devices are integrated here. So it consists of 3 layers, so that on the top you can find the cube and the spacer layer, and then at the bottom you have sensors and the interface to the outside. And this is good for a alpha fetoprotein detection, which is the protein in the liver cancer cell, and it consumes a nanoliter size of a sample, not even the micron size. And the size of this device is in a few millimeter in each side. Okay? And it displays a 5 millimeter watt. And as in the right diagram, you can see the 3 the holes for the inlet and the outlet of the bead and the sample. Then at the center, you call it as a bead storage area and the reaction chamber. And you can find a lot of pillars, which is about 30 micron, thick, wide. A lot of pillars for the microfluidic, the operation of the beads. So that the beads are inserted from the bead inlet and then move to the outlet, and then there is a chemical reaction, at the center while it's moving, and then it comes out. Okay. So you can see the cross section of those temperature sensor and the cross section of those pillars, which is 30 micron width and 5 micron space. And then on the right side, the bead is coated with some biomaterials like streptavidin, and then it makes a anti-AFP. And if AFP combines with this anti-AFP antibody, antigen and antibody reaction, then it'll make a chemical change, and then it makes a fluorescence out of it. So we know that that they are combined, and so we can detect the signal, and then from the bottom, the AFP concentration to the output, you can see the change, in those output voltage. There is a phenomena occurred, and the sensitivity is a 33 millivolt for pH, and the resolution is 0.1 pH. And this is not my work, but the Nest lab, was merged to the Google. I think the deal was 3 billion, for this one. So it was a sensational, but this device is not, it's about 7-8 years ago, and it was not really a very sophisticated device, but somehow the deal was made, and that's a learnable automatic thermal controller. So it has some friendly the functions, like as in this chart, and then it has basically the Fresnel lens for human detection with IL, and then Zigbee antenna, and then Zigbee RF chip, and then light sensor, and then the optical sensor, temperature sensor, and PIR sensor. So a few sensors associated with that, and that's it basically. But it was a good example of the IoT. So I guess that's why the deal was made. So so far, I talked about some of the MEMS technology and their applications on the sensors. And again, these days, many people, approached me, how to, make, this technology useful, for their the business. So it's another emerging area these days. And so as long as with the fabrication tools, which needs a bit of a the investment, and this will this kind of technology will give a lot of opportunity to work with. And from this electrical engineering department, electronics, you can put a electronics all together. So the whole device with the sensors, and then the electronics are combined together in one chip, so that one team can do the whole thing. So but it depends on the application. For example, for that chemical biological application which I introduced, we work very closely with the people in the biology and chemistry, sometimes to the medical doctors. So that's another domain,
Yes.
collaborating with those people. Thank you very much.
Thank you very much, Prof. Kukjin, for great talks, MEMS technology for sensors applications. Yes, it is very, currently in this situations pandemic, so still growing. And as we know that people stay at homes, and I think many people also, like you mentioned just now about Nest Labs, Google Nest, it is very famous for smart home products, right?
Yeah.
Smart homes,
Yeah, right.
yes.
Yes.
Yeah. Okay, we received so many questions. 4 questions here, Prof. Kukjin. Okay. I will read one by one these questions from Mr. Didi Arianto. He asked you how to make lithium batteries last longer and prevent damage to batteries.
well, actually, it's not in the MEMS area, but how the question was how to use that battery longer, right?
Yes.
Battery. You cannot increase the capacity of the battery because it's already made and purchased. So the one approach you can do is to minimize the power dissipation of your device. And MEMS is pretty good in that sense because in many cases, MEMS does not flow the current. The voltage is applied, but if you if you use the charging, the charge as a medium, then there is no current. So power dissipation is minimal. So in many cases, MEMS are isolated so that it gives a very minimal power consumption. So that makes the battery last longer. So that's why the ball, or other applications of MEMS, the last longer. But for the ICs, that's a different game.
Okay. Yes. Okay. Thank you. Another question is from Mr. Lalu Samsul Halid. So generally, what is the biggest challenge in developing MEMS sensor?
Yeah. Well, that's always a good question. If I get the same question, let's say 20 years ago, I would say the equipment is the most challenging. But nowadays, most of the equipment available, with advancement. So the biggest challenge is to find a killer application. So like a pressure sensor, the whole market is a few $1 billion. But if I go to Samsung, big company, they are talking about $1 billion per piece. I mean, $1 billion of the revenue out of one piece of a product. But sensors, you are talking about less than that. So that's a one challenge. So for a startup company or for a medium scale company, it's a very good item. Okay, but for a big company, sometimes it may not work. So the challenge is to find the killer application now. But people are getting into the mobile applications like RF MEMS, and that'll give you a lot of opportunity.
Okay, thank you, Prof. Kukjin. So we move to the third questions. I think Mr. Handai Saptaji, I think he is my student. Is it possible for emerging country like Indonesia to mastering MEMS technology? Is it eligible for SME, small medium enterprises?
Oh yeah, sure, yeah. Because there are many foundries, which makes fabrication, for you outside Indonesia, or even yeah. So well, if you think of the Korea 30 years ago, it was an emerging country. Now it's getting better, but it's still not in the good the country's level. So we are also being developed, and so well, the this is good for a small or medium scale industry. And so if you think of the well, if you look at the company list, then you can find very new companies there, and that's a like a Knowles company, that makes a micro speaker only, and that's in the top rank. So and again, Kurt Peterson, who basically initiated all the startup companies in MEMS area. Well, again, he made a well, basically he worked on pressure sensors, in the beginning with other people. So only one, item, can make a company there. Okay, so yeah, I think it's really possible.
Yes,
sure.
Thank you. Okay, question from Dr. Adi Wibowo. Could you give some details opportunity how the MEMS biosensor technology can support for solving COVID-19 problems? Bio.
Yeah. Well, actually, I made the similar talk in this last conference, and I introduced one example from the Caltech in the United States, that this to measure the what was called, to measure if a person is infected or not, for this COVID, the coronavirus. And it was a graphene based, and it was rather simple, the device, and the fabrication was not that difficult, there. So well, why don't you check with the paper from the Caltech on the COVID-19? I think the author was a Chinese, but anyway, so please check the paper that for this application.
Okay, Prof. Maybe two more questions. From Mas Grafika. So, what is the best communication method in MEMS sensors if we want to maintain low energy in minimum delay when we gather data from MEMS sensors?
I didn't get the answer. I didn't get the question. So could you repeat the question again?
Okay, what is the best communication method in MEMS sensor if we want to maintain low energy in minimum delay when we gather data from MEMS sensor?
Okay. Yeah. Well, the communication, sending the data, the wireless sending. Yeah. Okay. The communication tools are developed by other people, so it's not in MEMS area. So just the people, they adopt those technology, and as in the Nest lab, they use a BLE and Zigbee, those kind of the short distance communication. So in the IoT, you don't want to send the data in the far away. So just know the data in one node, is just sent to the host, so which is not far away. So you need a that kind of the communication in most cases.
Okay, thank you, Prof. Kukjin. So one more question. I think this question is almost the same. So I will summarize from Mr. Adila, Faisal Adila, and also Mr. Edward. So what's your suggestion for people with resources to be able to design, prototype, and develop MEMS technology? what is the minimum technology to develop my own MEMS there? And also, can we fabricate MEMS chip from local resource?
Yeah, okay. For the design, so it's like a designing the IC. So basically, you need an idea, and then you need a CAD tool, and it must. So like it's like a CAD tool for IC. So you make a layout, and then so the process is quite similar to the IC design, and then you send the tape to the foundry, for like a one in TSMC just started the foundry business in MEMS area, so we will see the development. And so there are a bunch of foundries in outside Indonesia, in many countries. So you can find you can send the tape, and then they'll make it for you. But for that one, well, either you can make a full wafer level, or you can make a about the 20 the chips or 30 chips, which is quite a low price. So either way, should work.
Okay. Okay, Prof. Kukjin. So, Prof. Wisnu, I think time is up. Yeah, it's already 10.
Prof. Kukjin, can I maybe request one question for you, because it's very interesting and yes.
Very great.
Actually, for example, in Indonesia, we have a center of microelectronic. Not in my university. We call central microelectronic in Indonesia, and in one located. We call the Bandung in Bandung Institute of Technology, and also collaborate with the research center. But the problem is the equipment is very expensive. And when we fabricate it, maybe when compared with the company, for example, for the Texas Instrument, for the Samsung and so on, maybe the output, the devices is not comparable. And what is your suggestion? Because actually it's quite expensive. And the second one is if possible, can we, for example, we make some design in the software in simulator in MEMS maybe, and then maybe can we? Do you have some suggestion? Is there any, for example, in Korea or in other country who can make some collaboration about we just design with the in the simulator because our background is computer science, and we can implement smart sensing and so on. So please give advice for me about the condition. Thank you.
Yeah. Well, that's a very good question actually, because it's very practical, and I can think of several ways. First of all, the MPW, right? Multi-chip wafer or multi-project wafer. Okay. So that the one wafer fabrication contains many different designs. So like 15 designers share the fabrication of one wafer. Okay, so that after the fabrication, the 15 designs come up from the same fabrication. Then that 15 people share the cost of the fabrication. That's called a MPW. And so when MPW started in 1978, I think, in the with the MIT and Caltech, in the United States. Now it's called the MOSIS, and they started that one MPW concept, sharing the cost, and then they go to the government, for funding, for user fee. Okay, like you mentioned, it's expensive. So the government United States government, developed a specific project, for supporting those usage fee. Okay, so when I was in University of Michigan, one professor was a contact professor, coordinator, and he makes a proposal to the MOSIS and get a funding from the MOSIS, and that funding comes from the United States government. So it's not a simple one, but you can persuade your government. That's one way. Or you can make an international collaboration, between universities or sectors that you have an idea and the implementation is done in somewhere else, okay, for you. Then that's another way, that's a, so you make a team with a, your team for idea and another team, another set of people, outside Indonesia for the fabrication or realization. So that's a international collaboration. And so, yeah, well, I actually I had a couple of experience with Malaysia.
With Malaysia,
a long time ago, and with the same, the same problem, same issue. Yeah, and so yeah, it's that's possible, and so. And again, the it's not cheap, but I could think of those two.
Yes. Okay. Thank you, Prof. Kukjin. And maybe please welcome to Indonesia. Maybe next year, I hope COVID will be disappear and you can come to Indonesia and discuss directly. Yes, special invite to Prof. Kukjin. Okay, thank you, Prof. Kukjin. I return back to moderator Dr. Nia.
Okay,
thank you very much.
Give applause to Professor Kukjin. Thank you very much for the great talk. Thank you. Will we have a photo session, Prof? No?
Photo session maybe possible.
Yes.
Okay.
Mas Hamid, Mas Robi, could you please help us?
Okay. Let me guide the photo session. Let me count 1, 2, 3 and smile. Okay, once more. 1, 2, 3 and smile. Okay, thank you.
Thank you very much, Prof. Kukjin. Okay.
Thank you very much.
Yeah.
Stay safe
and stay healthy in Korea. Okay.
Yeah.
Okay.
So the other one, maybe Prof. Kukjin, I will send the paper, my student paper, as a professor, visiting professor discussion. And maybe I will put also Dr. Nia name, co-author, and then maybe please we will still prepare 1 or 2 weeks. Is okay. I will I will send to you and your team. Okay. Thank you very much, Prof. Kukjin, for your support, for your help.
Thank you very much for this.
Thank you all the participants. Okay, we will have next sessions this evening with the title Autonomous Deep Learning for the Complex Data Stream from Dr. Mahardika from Nanyang Technological University, Singapore at 3:30 p.m. Indonesian time. So please stay tuned. Mas Hamid or Mas Robi, could you please share the link for this evening's talk about deep learning to the attendee here in the chat box?
Yes, of course.
Okay. Thank you, Prof. Kukjin. See you. Stay safe and healthy.
Bye-bye. Yeah, thank you.
Bye.
Thank you, Prof. Kukjin.
Right.
So participants, you are invited to join our next sessions today, this evening, on autonomous deep